Thank you. I'm going to talk about effects of imperfections on SolidWave gyroscope dynamics. So this work is a part of DARPA microrate integrating gyroscope program, and the goal of this program is to design novel isotropic 2 degree of freedom resonators for use as gyroscopes. So as we see on the left, we see a 3-dimensional SolidWave gyro, which is known as the hemispherical resonator gyroscope. And these have been in use for a couple decades now, and they are the gyro of choice for the spacecraft. So the aim of this research program is to design miniature versions of this gyro, just the one like the one shown on the right here. So the goal is to create inexpensive miniature versions. And when the program started, the researchers anticipated that microfabrication imperfections would limit the sensitivity of their devices. And this turned out to be true. So our goal is to understand what these perturbations are and how they affect the workings of these type of gyros. So what's a SolidWave gyroscope? So an axisymmetric body supports pairs of vibration modes which have the same frequencies. And a simple vibration of the device can be written as a linear combination of these two model shapes. So the coefficients, time-dependent coefficients Q1 and Q2 here are like the coordinates of motion. And the equation of motion for this system is governed by this 2x2 lump model. So ignoring the middle term, we have two identical harmonic oscillators. So when the device is rotating, the gyroscopic term, the middle term, splits the frequencies of these pairs of modes, these twin modes, by a small amount. And as a result, we have some changes in Q1 and Q2. So for the non-rotating case, in general, Q1 and Q2 follow an elliptical trajectory. And when the device is rotating, this elliptical trajectory also rotates. And the rate of rotation for this elliptical trajectory is actually proportional to the rate of rotation of the device. And it is device specific. And this is the basis for the SolidWave gyro. So what happens when we have geometric imperfections? So let's look at a simple ring resonator. So here on the top we have a perfect ring and two deformed rings. One like triangular, the other one is deformed as a square. And on the bottom we see these vibration modes. In the first two cases, these pairs of modes look like they are rotated versions of each other. But on the third one, they don't look like each other. If you look at the dynamics picture, we see that so the top row corresponds to a non-rotating case, and the bottom row corresponds to a rotating case. And the order of columns are in the same order: perfect device, triangular deformed, and square deformed devices. So in the first two cases, we see a nice picture. And for the third one, we see a mess. So if we just integrated the trajectory longer, the trajectory doesn't look like a rotating ellipse or a line. So why does this happen? So in order to understand why it happens, we first have to have a way of describing these vibration modes and the perturbation modes in some way. And for an axisymmetrical device, the natural way of doing this is using just Fourier analysis. For the vibrations modes that we have looked here, we have our radial displacements just like cosine 2 theta. So we say that this vibration mode has an azimuthal number m equals 2. So we refer to vibration modes with the letter m. And the perturbations that we have for the ring resonators had these radial deformations of the thickness actually in cosine 3 theta or cosine 4 theta type of functions. And we say that these perturbations have p equals 3 and p equals 4 azimuthal numbers. So a more general perturbation can just be decomposed into a Fourier series, and each perturbation can be considered separately. So we need to understand how these vibration modes and perturbation modes interact. So for that purpose, we took the same ring resonator and simulated it by increasing the amplitude of the perturbation and looked at the frequency splittings of these modes for m equals 2, 3, and 4 vibration modes. So the top figure shows when we have a perturbation at p equals 2m, and we see a nice linear splitting of those three modes. The bottom picture shows when we have a perturbation at p equals m, and we see a quadratic dependence of this splitting. So our observation is p equals 2m has this first order splittings, p equals m causes second order splittings, and if p does not divide to m, then we have no splittings at all. For example, for the triangularly deformed device, p is 3, and the mode we were looking at was 2, so 3 doesn't divide 4, so we saw no splitting and the performance looked nice. So in our paper, we list a set of rules about how these vibration modes and perturbation modes interact through an algebraic equation. And similar to this discussion, in atomic physics and molecular chemistry, the energy levels of the system also splits in a similar manner when you introduce external perturbations which have a particular symmetry. So why do we care about these perturbations in the first place? So if we know which type of perturbation affects our working vibration mode, then we can make design decisions based on our fabrication method. And here, in this table, I just give a couple of examples for different fabrication imperfections in microprocessing. For example, if we have a mask misalignment, then we have a perturbation like p equals 1. Or if we are doing some chemical etching, then some over or under etching would result in p equals 0 type of perturbation. So the p equals 0 perturbation wouldn't really destroy the axisymmetry of the device, but it would shift the frequencies. We also end up p equals 4 type of perturbations because of the crystalline nature of the silicon wafers that we are using. Or if there are some misalignments of the planes, then we might end up with p equals 2 type of perturbations. So when researchers started working on this project, what they realized was, unlike the conventional SolidWave Gyro, which works with vibration mode m equals 2, they realized that m equals 3 mode actually works better. And it was sort of confusing in the first place. But after looking at the typical fabrication imperfections that we have, we don't really see a perturbation like p equals 6, which would have splitted the m equals 3 mode linear at first order. But we do see p equals 4 mode and p equals 2 type of modes and p equals 1 type modes more often. So as a result, the m equals 2 mode is more sensitive to the fabrication imperfections for the miniature versions of these SolidWave gyros. Okay, so far we talked about using Fourier analysis to qualitatively describe how the modes would split. Now, we can also use the same Fourier analysis for the computational tools. So we can use the same selection rules to achieve a speed advantage by just considering the blocks of system matrices which would be related to those particular modes. And also, we can use structured meshing for better accuracy. So how much accuracy do we care about? This is already specified in the DARPA AMRIC program. For example, in the first phase of the program, one of the goals was to design devices which had these three modes separated by at most 1 Hertz. So as a result, researchers created devices on the size of millimeters, which work at kilohertz regime. And the challenge was to get that device out of the oven just with less than a 1 Hertz splitting. So here I show a simulation of a resonator called birth bath resonator. So a birth bath resonator is like a toroidal shell cut in half. And here I have simulated it with COMSOL. And after just drawing the geometry, pressed on the automation feature of COMSOL, and as a result, we get a mesh which contains triangular pyramids. Unfortunately, when you do a vibration analysis on this mesh, you see that the frequencies are not equal for those twin modes. And for this perfect geometry for your finite element tool, you end up having a couple hertz difference in these vibration modes. So, and remember, this is for the perfect case. So we can use, rather than using this unstructured mesh, if we use a structured mesh by creating quad elements on the cross-section and revolving it around the symmetry axis, then this problem partially goes away. So we end up having modes much less than, very close to each other, maybe millihertz type of difference in this case. But this mesh that we created actually is not good for every m and p values. The reason is the number of cells we are using for the revolution creates a mesh which might or might not be capturing the symmetry of the vibration or the perturbation mode together. Or if you are looking at multiple modes or mode couplings, then even a structured mesh in this three-dimensional way might not give you good accuracy for the perfect case, perfect geometry. So if you want to consider imperfections on this geometry, then you would have to go and deform this structured mesh. And if you are deforming, when you are deforming it, you again might end up introducing these spurious splittings. So in our simulations, we used this, we exploited the axisymmetry of the device and just worked on the cross section, which allowed us to use any element type on the cross section. And as a result, our 2.5D type of approximation captures the axisymmetry of the device fully, and we don't introduce any spurious imperfections which would come from a three-dimensional mesh. So here, I just shown you a picture of a hemispherical device with a lip around it. So to conclude, we took geometric imperfections, mapped them to a perfect domain, and after creating the system matrices and computing the eigenmodes of the system, using projection methods, we can compute the 2x2 coefficients in the lump model, which is described in our paper. And also we come up with an algebraic rule to describe which modes, which vibration modes interact with which perturbation modes. And also we use these selection modes to create much lower dimension matrices, and our solvers work faster in this case, and also more accurate. So I would like to thank our contributors at Cornell EC department, Sunil Bave, and his one of his students in his research group, Laura Figley, and our funding comes from DARPA EMRIC program. Thank you very much for your attention.